Welcome to a new test and teardown video. This time it's a Radiometer type RV24 DC AC voltmeter, but it can also do ohms. So I would call this a multimeter. We got some different inputs. An external probe for AC. I believe this one just contains some filament voltage for driving an external tube rectifier, of course. And this one is for higher speed of AC. And inside there will be a little tube rectifier. And that will be the DC. For DC voltage and DC ohms. I was lucky to find a schematic on PEEL.DK. I will put a link in the description so you can find all the nice information. As you can imagine, look at the size. This is huge and it's 6.7 kilos. So it's really heavy. I mean, you cannot compare this to something like this. This is what we use today. And it's, what, 55 years ago or something like that? That's it. That's a little bit amazing. This is a real nice thing. Normally Radiometer got contacts, and then you need to have the right cables, but here the cable is here and the little cable winding holding thingy. I got some, I don't know exactly what that is, the idea. I got this sticker here made in Denmark, and this is the A, so this is the first revision of this unit. And also on the top of more or less all Radiometer units, you will find this made in Denmark by Radiometer in Copenhagen, Northwest. Yeah, we better open and have a little inspect. It's of course quite dirty, look at that. And the color of the circuit board and everything down there is just really dusty, so to speak. I better go and wipe it a little bit clean. So we got here in the amplifier board, we got two ECC81s. They're still from Philips. And I really find this super funny, the way this is implemented with the switches in two different layers like that, with the long sticky. I mean, there's also another little mechanical problem. All the switches here at the front, they kind of grind a little bit here on this metal plate. See all this? So either something here is not mounted correctly, or there's, oh yeah, see, there's plenty of space under the switches, but not over the switches. This is not how it's supposed to be, right? And yeah, so after a little clean, I will go and look a little bit more at all this. First of all, I want to try and see if I can fix the little mechanical issues with all those buttons here being pressed towards this edge here of the front. And it was super easy just to remove this, the 6 screws here at the front. And it turns out, if I make the holes here a little bit bigger, I can actually adjust the front a little bit up. But if I do this, the front's gonna hit this and that. So that is also a problem. Seems like the top row here, they're just dangling a little bit loose because there's nothing to steer them. And this part here is also just held in place by the front plate. So I think I want to loosen those spacers here as well, and then try and move those a little bit as well, and just to see if I can move the margin a little bit. And I can see I'm not the only one who tried to fix this. See, you can see somebody sanded or filed away a little bit here on the top. And of course they didn't sand anything on the bottom part. So this, I'm not the first to see this as a problem. And also I realized the two potentiometers here, this one barely moves, but this one is, yeah, very, very stuck. So that is also a little bit of a problem. I do find a huge pleasure into solving all those little mechanical issues as well. So let's try and show this. See, here's the distance now on the top and the bottom, and it's almost in the middle. And now there's no scraping. Now we got space. So all I had to do is, of course, take everything out and then clean it super nice and fine. Try and push this front plate all the way up while tightening all the screws. Try to push this part here with the circuit board as much down as possible, and then tighten the screws. But then another little trick, in each side I pushed in a tiny little piece of plastic here, and it now pushes the circuit board a little bit down. It is actually supposed to touch this one, and it is supposed to be a little bit bendy here, and this is what holds everything here. But eventually it's gonna get softer, it's just bent a little bit more or less, and then you have this problem. So now I just added a little extra here, and then I will add a little drop of glue, and now it is done, and I can proceed my little adventure with this one. Let's look a little bit on the specifications. I think the most impressive is actually to go all the way down to the frequency response. So it's within 1 dB all the way from 10 Hertz to 50 megahertz. I mean, you gotta be impressed for a unit from 1964 or something like that. And I think the reason for this is so wide frequency response is the signal path on the AC input is more or less just a capacitor, and it goes straight into a rectifier diode system, and then it becomes DC. It also says, if you look a little bit further down here where it says calibration, meter reads the RMS value of a sine wave, but responds to the positive peak value of the input voltage. So that means it's a peak voltage meter, and the readout is just calibrated so that the readout corresponds to the RMS value. So I think that definitely explains the range. On the next page of the specifications, there is a little fun thing, and this is of course only related to the ohm meter, and that is this built-in 1.5 volt battery. And they further down in the next line here, they say a battery is a 1.5 volt, and then the size. This is just the specifications for the battery. It's a size thing. So that means, why do I buy a 1.5 volt battery that is 33 times 61 millimeters? I mean, wouldn't it be easier to say what this cell is kind of called? I would call this a D cell. But that is just the weirdest. By the way, if we look down in the left, bottom left, it says tube complement. Okay, there's an error. What? Only one EAA91 rectifier diode? No, we got two of them, not one. So that is yeah, that's also funny. Here's the block diagram in AC mode, we got two different AC inputs. You can use an external AC probe. That means the rectifier is external, and then there is a filament voltage in this connector to the external AC probe. And this will of course give you an extended frequency range, or you can go directly into the built-in rectifier tube system. It's called AC direct, as shown here. In DC voltage mode, we need to use the high and low banana jacks, and it shows the input impedance here. There is 25 mega ohms to chassis, so you can have 400 volts floating to chassis and to mains ground. And here is the block diagram in ohm measurement. And of course, everything is now recalibrated. All the ranges and stuff there are now modified to read the ohm value. It's sort of shown a little bit here with how it's going the other way around the different attenuator systems. And there you have it, a battery with a series resistor. That is, of course, the different ranges for your ohms. And then it, of course, just measures what is the voltage over that resistor you're measuring. Quite simple. But it definitely revealed there is a built-in battery, and that is something that requires our extra attention. So after a lot of cleaning and fixing all the mechanical issues, and of course fixed also the two trimmers here, or the zero and the gain here, and so it looks much more presentable. It's better for the video, isn't it? To look nice and shiny. But here it is, our 1.5 volt battery, as they call it. And I find it real funny the way that they have made this. Look, there's a outer plastic cup, and it's completely closed in the bottom here. And that is so good thinking. I mean, I really hate built-in batteries. I mean, I cannot say how bad I think about all this, but when they really insist of having a built-in battery, it's still the best solution to have a plastic cup like this, because when the damn thing leaks, all this splat is self-contained in this. It doesn't drip down here and destroy all the ranges and all the switches and this trimmer here and everything like that. So this is what a lot of other companies could have learned a lot from. But to be honest, I really would have, I would have solved this somehow else. We got a transformer, we could make a little extra winding, make a little DC voltage. I mean, diodes, they were really invented. I mean, why would we do a design with a built-in battery if we could, for whatever reason, solve it? I mean, what? Damn it, I hate it. And the thing is, I just checked. This unit was not used for at least 10 years. And I measure 1.5 volt on that one. So now I really want to open it and have a look. Also, how do you do this? I mean, you need to unscrew something. And then why isn't it marked really loud and clear what is positive and what is negative? So I took out the old battery and look at this little number. Here it says it's from 2005. So that is 20 years ago. And look at that. Brand new voltage. And thanks a lot. And no leaks whatsoever. Only a tiny little rust here, but it's probably just from humidity. There's no corrosion. There's probably a better idea to put this back compared to putting in a new one, especially if we talk about Duracells or something like that. It will be the leaky nightmare. So I actually want to put this back. And let's play with that one. A little bit annoying thing is it isn't marked how this is supposed to go, positive, up or down. I don't find any information about that. And also I'm not super happy about the negative is the white and red wire and the positive is the blue wire. At least this is how it was when I got it. I'm not happy about that, to be honest. And no information about... Yeah. Well, let's see. Here is a nice bottom view. And here we got our two EA91 rectifier tubes. And of course they're connected to the AC input. See, here is our AC input. And it goes to the diodes and all that kind of stuff. And this is our external probe input. I really like that all the trimmers, they are neatly named and numbered, and in the manual it says exactly how to tune each and every one of those. And it's because every switch and every little range, whatever you do, is connected via a trimmer, so you can individually tune and align everything so nice and easy. Don't you just love this circuit board layout? Everything here is done with tape on plastic film. That is how you do it. Let's look a little bit at the schematic. Here is the whole schematic of the entire unit. And of course this is very big and there's just so much. I want to zoom down to the lower left corner. And here at the lower left snip, you'll see something that is, I think, a little bit interesting. And that is this AC input, the AC diode tube. And this is 1/2 of the EAA91 tube. So we got 2 diodes in one tube, and we got 2 of those tubes. So we got 4 diodes in total. I will get back to this in a few minutes, but just try and remember this. Okay, then we got the 2 AC switches, either AC direct or AC probe mode. In both of these modes, we can now see how the signals from the diode rectifier here is routed up to the different input attenuator systems and all that. This is not super interesting for now, but this is just the point of the input here, right? Here we zoom in on the upper right corner of the schematic, and in the very upper right we see a rectifier and a high voltage capacitor. This is the anode supply, the high voltage, and look at that. They didn't even super rectify, super filter, regulate, or any double inductors and stuff like that, as you always see in tube equipment. And why not? Because the output of the high voltage simply drives a differential amplifier made with the tube called 201. So tube 201 is a differential amplifier, and that means it really doesn't matter what is the supply voltage. It can be full of ripple. It's only amplifying the difference, and I really like that idea. Let's talk a little bit about the filament voltage. See, here I have marked the 2 tubes, the differential amplifier, and I have marked with red how they generate the filament supply for those 2 triodes. And see, there's a Zener diode, and that means the voltage for the very important differential amplifier's filament is regulated, it's stable, and there is a constant temperature in that cathode, and that means the gain is constant and regulated and all that kind of stuff, so it's not drifting, and this is very essential for this instrument. Here I have marked the other 2 tubes with blue, and those are just cathode followers. So they just convert the high impedance output from the differential amplifier. And because there is no voltage gain, it really doesn't matter if this tube is hot or cold, or if it's drifting a little bit with temperature for the filaments. It's still going to amplify and help with the impedance amplification from the differential amplifier. Down here we see the zero system, the offset for zero balancing, and you have of course a trimmer on the front of the panel, and that is of course because this is a tube unit and stuff will of course drift with age and whatnot anyway. So this is how you simply adjust your offset. But here is the real magic thing. You see the two diodes down here I've marked with red. It's the other three diodes. It's there's the half of the first tube I talked about earlier in the input rectifier system, and then there's another extra tube with two extra diodes. And look carefully, all three diodes, they go in series, and you have two trimmers and the two switches. Like I talked about earlier, those two switches, they are now enabled when you are in AC direct or in AC probe mode. And in those two modes, they now take the offset voltage generated by those two diodes, or three diodes in series, two tubes. And that is because of temperature compensation. And now by having three diodes in series, they have too much compensation, and by adjusting the trimmers, they can go down to little and then find this sweet magic spot of super accurate stability. I find this so magic. And they couldn't have done this with only one tube containing two diodes, because then what if there is in this compensating tube in the other half, if there is just a tiny little bit too little, then you don't have any more to adjust from. So you need something more. And then they just took two extra to have plenty. But you could have done it with only one, of course, one extra. So let's try and see what happens when we power this on for the first time. Of course, it goes pretty well. We got a red lamp, and I am now in direct and 10 volts, so it should be this input, and it's in the warm up stage, so I expect the needle to go a little bit up and down and what not. Okay, so yes, this is the 0, and the idea is you just put this for 0, and then you have already handled all the different DC imbalance. So this is low, it's not responding to that, so that is good. And here is 8 volts, and we are of course in the 10 volts, so I expect it to go around here, right? Oi. A little bit too much, but that is probably within the accepted tolerance. I of course expect to find the trimmer and figure out if I can do this more accurate, but at least it is working. And let's go back and see if it goes to 0. Haha, you see, we need some more warm-up time, and now I can tune this back to 0, and I should probably wait a little bit and try and do this again. And now we got the, it's still changing a little bit, but this is our 8 volts. Look at that. I think you need to wait a lot more. Yeah, now we are there, definitely. So that was the first range test. Yay, DC voltage works a little bit. So I just looked this up in the manual, and it is trimmer number 8. That is the 1 volt range. And if you wait long enough, you have now a 0. The 0 takes quite a long time to get back to. So let's try and apply my 0.9 volt. And then it goes. I think it's also the angle of the readout. It's a little bit too much now. And I want to show you the problem with the trimmers. And this is actually all of the trimmers. So if I try and touch the trimmer a little bit here. See? It just disconnects, see? And I go down real slow. It goes like that. Now it's all the way down. Yeah. I mean, I can't do anything. Okay. I should just massage it a lot more. Oh, I only want it to work in this range right here. And get it to 0.9 maybe. But it's like, I just touch it a little bit. And then it's, that was lucky. Wow. One range is solved. Oh yeah, so it's gonna be a long day if I need to change all the trimmers. Did I show you how many trimmers we got? Yeah, all that and a little bit here. It's the same quality. We got some more hidden in here, by the way. And I don't know. But that is, I think, the status so far. So since this thing is using a nice battery that is actually 1.5 volts, let's try and go into ohms. And this is times 100. And the idea is you adjust the open until you have a perfect readout here. Like that maybe. And what I got here is a 1K resistor. Let's try and connect that one. And of course it reads 10 times 100 is 1K. Isn't that lovely? So it's actually accurate. Isn't that lovely for a unit that old? So let's try the AC volt mode. So I screwed in a little adapter here so we can go into a B and C connector. And what we will learn from this readout here is the volt, the AC. It says here 1 volt AC only, 3 volt AC only. So that's the two lowest ranges. So let's go for the next one, the 10 volt RMS, and it will be this one. So this is the one that we're using, okay? Here is 1 kilohertz, 5 volt RMS, and if I click, here we go. And it is a little tiny itsy bitsy part low. Let's double check the 0. And if we wait long enough, it should go back to 0 like that. And it's almost there. I should try and see if I can find that trimmer for AC volts and then the range 10. I expect there is another one for AC and another one for DC, I hope. I think I was able to figure this out. This is, of course, extremely bad explained in the manual about the AC calibrations. Why the hell didn't they make it exactly as nice and fine as the DC calibration? But anyway, so this is AC, so 10 is full, and I give it 5, so that is fine. Let's try and disconnect the AC input, and it goes to 0. Okay, so let's go back to the 3 volt AC, and now we need to use this scale, right? And then we give it 3 volt RMS at 1 kilohertz, and it should go around here. The reason for those extra scales, that's because they're the tube rectifiers they're using. They are far from ideal diodes, so there is a different curve, and that is why you just have extra curves to compensate for that and make it good. So now we have the 1, let's put in 1 volt RMS, and it should go down to this scale here. And now you see the difference in the linearity. If we were supposed to use this scale up here, it would have been wrong. But now they got a good scale down here that works perfectly fine. So here's 1 volt. And we use this scale. Can we give it 0.5 volt RMS? And we should be here. And that is also correct. So that means I did it right. I've been poking around with all the trimmers down here, giving them a little bit of contact spray and then a lot of massage, and I was able to hit the exact correct point where it had connection and was reading correct. But any other place it will be random readouts. That's just how it is. But anyway, at the moment I feel the calibration is good. Definitely a thing to do for the future. Put in a new battery and put in new calibration trimmers so they are nice and fine. But that is what I wanted to show you about this cool old Radiometer multimeter. I hope you had a little bit of fun. See you. Bye.